We'll be speaking about quality of stringy E-functions of Pfaffian double mirrors and with related results.
All right, thank you. So my talk will be fairly slow and fairly elementary, so we'll try to keep it pretty basic. So I start by explaining the example of Pfaffian-Grassmannian double mirrors that originally first appeared in a paper of Rodland in late 90s, 98 maybe. So it goes as follows. You start with a complex vector space of dimension 7. And you pick, so this is part of the data, then you're going to pick a generic 7-dimensional subspace of the space of skew forms on V. Think of it as just picking random 7 by 7 skew symmetric matrices. Thank you. All right. And the observation of Rodland was that to this data you can somehow associate two different Calabi-Yau threefolds. Let's call them XW and YW. So here they are. XW will sit inside the Grassmannian of 2-dimensional subspaces in V. And it will be such 2-dimensional spaces in V that W restricts to them as 0 for all forms in my capital W. So in other words, what it is, it's a complete intersection of 7 Pluker hyperplanes inside the Grassmannian. Complete intersection of 7 Pluker hyperplanes in G27, G2V, whatever. The thing is, I mean, vanishing at a 2-dimensional space for skew form is just one condition. So you have 7 linearly independent conditions that drops the dimension from 10 to 3, and by Bertini, generic W will keep it smooth. So it's a smooth 3-dimensional Calabi-Yau manifold. Calabi-Yau is by adjunction. YW is a little bit more sophisticated. What it is going to sit inside PW. So PW is lines through the origin and W. I'm using that convention. And what these are W's up to scaling such that the rank of this form is at most 4. Now, a rank of a skew form is always even, so generically a rank should be 6. But it drops down to 4 in codimension 3 locus. And if capital W is generic, then this actually will be equal to 4 because you're going to miss the rank 2 locus. It's a little bit more work, but essentially, because W is generic, YW is also smooth. N is also Calabi-Yau of dimension 3. Well, whenever you construct two varieties from the same set of data, you expect some kind of relation between them, and that's reasonable. In this case, both of these XW and YW, they share, for example, the Hodge numbers are the same. So H11, H12, for both of them is 1 and 50. You may ask whether XW and YW are isomorphic or birational, and they're not, and which will be important later. So I want to make this remark. So XW is not isomorphic to YW because for a generator of Picard group, you have D on XW cube is 42, and D of YW cube is 14. So just the intersection numbers of the generators of Picard are different, which means they're not isomorphic. And a little bit of work theory tells you that this implies that XW, YW are not birational to each other, because they have Picard1 and the birational Calabi-Yau threefolds are connected by flops, but there are no flops in Picard1. And moreover, they're not even stably birational because there are Calabi-Yaus. So there is this MRC fibration, which is a birational invariant, so the base of it would be birational to each other, and so this shows that they're not stably birational. Why do I call these guys double mirrors? So for this, I have to go into a little bit of physics. More precisely, string theory. I mean, it's debatable whether everybody will call it physics, but I will call it physics. So what happens if you think of this family of Calabi-Yau varieties XW? There is a heuristic mirror along the lines of this Candela's, Morrison-Plesser kind of orbifold constructions. It's just heuristic. So there is some kind of one parameter family of Calabi-Yaus. And there's a statement that two different degenerations of this one parameter family give mirrors. One gives mirror to XW, one gives mirror to YW. Mirrors in the heuristic sense of doing some kind of Picard-Fuchs calculation for this one parameter family and recovering some instanton numbers, some numbers of rational curves on XW and YW. And that was done by Rodland. And so in this case, when you have two families of varieties which have the same mirror, this is what I call double mirror. So that's the meaning of terminology. And in this case, you expect XW and YW to share a lot of features. In these easy cases, they just happen to be birational, but this one is the interesting one. They're not birational. As far as I can tell, there's maybe just a handful of such examples, and this is the first example where you have non-birational double mirrors. All right, this is physics.
Derived equivalent K3 surfaces.
They should be. Well, I mean, you would have to check and see, right? I mean, but probably they would be double mirror.
Double mirror symmetry.
They will give you a huge number of examples.
Which are not birational.
Well, that's true. You're right. Yeah, you're right.
Calabi-Yau treatments around finite from animals.
Yeah. It's worse with, yeah, okay, right. Yes. Yeah, I mean, so, right, anyway. So now coming back to mathematics. If you believe Kontsevich homological Miller symmetry, then derived category of coherent shifts here should be equivalent to category, derived category, Foucault category here, and same for the YW. So XW and YW should be derived equivalent. And indeed, this was verified independently by Kuznetsov and me and Calderaro. In around 2006 or so. And what I'm going to talk about today is the preprint from last December, which says that XW and YW are pretty close to each other in the Grothendieck ring of varieties. So their difference is annihilated by this polynomial in L, where L is class of affine line in the Grothendieck ring of varieties over C. And that in particular then implies that L is a zero divisor in the Grothendieck ring of varieties, and I basically just stumbled upon it by doing something else, which is I'm going to describe where this thing comes from and so on. Yes. Yes. Absolutely. Right. All right. So before I move on to explain how this works, I want to sort of stake the claim for, yes, yes.
One is a zero.
No, not that I know. I actually, I would imagine that this already might be zero, but I just don't know how to prove it. It might be true, it might no. So basically, I really don't know what it means. I'm sure that L plus 1 is probably irrelevant, but you know, L minus 1, I really don't know. Okay. So let's see. So there are generalizations of it. And the first generalization is replace 7 by n. And to have the dimensions match, I want an odd n. So first generalization, replace 7 by any n greater or equal than 5, odd. And then you have XW inside the Grassmannian such that, okay, so just a complete intersection. And then you have YW, which are of these forms in capital W. Capital W is in H2V. Now this dimension n, and this is dimension n generic. So the rank has to drop to n minus 3 or lower. And in this case, XW is smooth. But YW is generally just Gorenstein. I mean, if n is large enough, like 11 or something, and they have the same dimension n minus 4, then the theorem whose proof I'm going to explain, but not in a whole lot of detail, I'm going to focus on that expression more, is that the Hodge numbers of xw are equal to stringy Hodge numbers of yw. And this is my joint work with Anatoly Libgober. And the history of it is that we set out to work on this, and that thing on the right was just an accident. Or rather, we set out. Huh?
So what's the dimension or the canonical class of these XW, YW?
Oh, the Calabi-Yauss.
Oh, they're called.
Yeah. Yes, they're both Calabi-Yauss.
Sorry. Oh,
That's fine.
Dimension.
Dimension and -4, each of them.
Ah.
That's fine. So you can do something even a little bit more drastic, and a lot of it goes to Sasha Kuznetsov. So I mean, this you can do something more drastic. All of it. I guess in his terminology, a lot of it will be called homological projective duality. So it really is related to it. So you can do something where instead of Grassmannian and Pfaffian, you look at other secant varieties of the Grassmannian. So there's some kind of generalized Pfaffians. Let me explain what those are. So you pick n, which is odd, greater or equal than 5, and pick some k between 1 and then -3/2, where k equals 1 is the old case, and we're going to generalize it. And then I'm going to look at xw inside something I'll call Pfaffian of 2kV dual. These are forms in a P wedge 2V which have rank at most 2k. And YW will be sitting inside Pfaffian of n-1 minus 2kV. And W, so again, V will be dimension n. W will be dimension nk in wedge 2 of V dual, generic. And so XW, one Calabi-Yau variety, will be a complete intersection inside this Pfaffian. So you intersected with the annihilator of W, and YW is here. So in particular case, when k is equal to 1, you have, for example, a Pfaffian of n-3V. So these are forms on V of rank at most n-3, which sit in W. And the other side are forms of rank 2 on V dual, so elements of Grassmannian of 2, V, which sit in annihilator of W. So now here, everything looks very symmetric with respect to switching V and V dual, W and annihilator of W, and K and n-1/2 minus K. So the claim is that, again, XW and YW are double mirror. That's a heuristic claim. There is no math to it. But the theorem is that stringy Hodge numbers of XW will exist and equal stringy Hodge numbers of YW. So stringy Hodge numbers is some kind of gadget due to Batcherev. The way it works, if your variety has a Crepant resolution, then it's just a Hodge numbers of any such Crepant resolution. It doesn't depend on the resolution. If there isn't, then you do any kind of resolution, log resolution, and then you weigh the strata with a certain polynomials, and you hope that what you get is a polynomial, and then that gives you stringy Hodge numbers. And this is again joint with Anatoly Libgober. Okay, so I'll leave this for now, and I'm going to try now to explain how this argument goes.
Okay.
Well, you have to look at ICM talk of Kuznetsov, right? The point is that even in this case, one of them is singular, the other one is smooth, right? So you cannot say that derived categories would have to be the same. What you expect is that there is some kind of non-commutative Crepant resolution of both of those derived categories, and those should be equivalent to each other, right?
Yes.
But it's not clear at the moment how to construct those resolutions. I think maybe in that case it's clear, right? But maybe not here. For small n, you can do, okay. So if you wish, this theorem is a good indication that those Crepant resolutions should exist. Because this one would be more or less related to the Hochschild homology of those categories. All right. So let me draw a little picture and say that the main idea is to use something known as the Cayley hypersurface trick. And this is an old trick that is basically allows you to go from complete intersection like this to just a hypersurface where you introduce auxiliary variables. And you look at the geometry of the hypersurface, and inside the geometry of the hypersurface, in some ways, there sits the geometry of the complete intersection. So that's the motivation. So in my case, I have G2V, this 10-dimensional variety. Inside there's XW. There is a 6-dimensional PW. Inside there is a 3-dimensional YW. And I'm going to consider inside the product the hypersurface H defined as follows. So H is the set of pairs T2 and CW, where T2 is just a 2-dimensional subspace in V, so just a point in the Grassmannian, and CW is an element in PW, such that W restrict to T2 is equal to 0. So it's just one codimension one condition and the product. The idea is rather simple. I want to calculate the class of H in the Grothendieck group using the first projection and then using the second projection, and then compare. And roughly speaking, we get this up to some technicalities, which we will get into in due time. Okay.
The kernel. It's not T meets the kernel. It does.
No, right. So that's right. So if you know how the derived equivalence is proved, this is different. Right. I mean, that one you looked at. So, right. So here I'm actually looking in the product of the ambient spaces, not in that. Okay. Well, all right. So let's consider projection of H to G to V. This is where the usual Cayley trick comes from. Well, what is a fiber over T2? By definition, fiber of T2 are such forms in PW which are 0 on T2. So in particular, this fiber is PW, is everything if T2 is in XW. Because remember, XW was defined as the set where all forms from capital W are 0. And otherwise, it's some kind of CP5 inside PW, because you have one linear condition. What's important for calculations is it's not just some kind of, so this is actually gives you a Zariski locally trivial CP5 fibration as T2 varies. Okay. Now, I didn't really say what Grothendieck ring was. Essentially, you look at the formal group with generators, the classes of varieties, and when you have an open and closed, open subvariety with a closed complement, then you have this some condition, some sort of universal Euler characteristic, if you wish. And well, what you have is the following. You look at the parts of H over XW and parts of H elsewhere. And so then in the Grothendieck ring, class of H is this, plus class of the complement, that's G2V, minus XW, times class of CP5, which is the same as class of P5 times G2V, plus, so XW will appear with P6 minus P5, and that's exactly L to the 6. Right? L. And that's somehow the whole idea of Cayley hypersurfaces, that, for example, you could see the Hodge structure of complete intersection as sitting inside the Hodge structure of the hypersurface, but with this sort of Tate twist. I mean, you shift the degrees a little bit. All right. This is really nothing particularly interesting. More interesting is what happens when you do projection to PW. So I have my definition of the Cayley hypersurface over there. So let me think what happens as I look at the fibers projecting onto PW. So fiber over C small w in PW is a hyperplane in the Grassmannian, such that W restricted to T2 equals 0. So in other words, it's a Plücke hyperplane. Plücke hypersurface in G2V that corresponds to W. And it's very reasonable. A reasonable idea is that you can again try to detect YW by noticing that the isomorphism type of the Plücke hyperplane depends on the rank of the form that you use to cut out. If you cut it out by a generic form, then you get a smooth hyperplane. If you cut it out by something non-generic, then it will actually be singular at points which sit inside, and which T2 sits inside, and the kernel sits inside the kernel. And however, the isomorphism class depends only on the rank, because I mean all forms of the same rank look the same. So naively, you get the same similar statement that the class of hyperplane H is YW times class of the cut of G2 7 by form of rank 4. Because capital W is generic, so the rank is either 4 or 6. Okay, I guess just like this. Plus P6 minus YW times class of the cut by form of rank 6. Okay? When I say that this is just a naive statement, the problem is I don't have the risky locally triviality of the fibrations. It would be true if this fibration was the risky locally trivial, but I don't know if it's true. Maybe it is, maybe it's not. If it is, then you get a slightly nicer relation than the one I wrote. But there is a way around this technicality, and what you do, you pass to the frame bundle to get the risky local triviality. I'm going to pass to something I called H-twiddle, which is a principal GL2C bundle over H. And specifically what H-twiddle is collection of V1, V2, and CW. So V1 is an element in V, V2 is an element in V. CW is the form from capital W up to scaling, such that W of V1, V2 is 0, and V1 and V2 are linearly independent. So in other words, I just pick a basis of T2. So you get, on one hand, that class of H-twiddle is class of H times the class of GL2C. And that's class of H times L squared minus 1 times L squared minus L. And I kind of think, the usual count of in GL2C, you pick first vector freely, so long as it's not 0, and the second freely, so long as it's not in the span of the first, and it can be done the risky locally trivial way. And now, once you do that, the fibration over, so the H-twiddle can actually be cut up into pieces which project onto YW and its complement in the risky trivial way. So for example, let's say I'm looking at the part of H-twiddle which sits over the locus of forms of rank 4. So what you do, you can pick V1. You can ask, is V1 in the kernel of W or not? Being in the kernel of W, it's being in a C3 vector bundle. So again, this is a risky locally trivial C3 bundle over the locus YW, and you're just picking a non-zero element in it. And then if it's in the kernel, then V2 could be anything, and you can work that out against the risky locally trivial. Otherwise, V2 would have to be picked perpendicular to V1. But again, everything works. And once you pass to H-twiddle, you compare the two sides. And after very little calculation, the whole paper is 5 pages. You get this xw minus yw is annihilated to L to the 7 times L squared minus 1 times L minus 1.
Two bundle, just take the projectivization of the tautological bundle and do the same argument, and then instead of L squared,
So you mean just try to do P1 bundle? Let me think.
you will have L plus 1 additional.
That would be great. So how? I have to think. If I can. I would have to check if I get the risky local triviality.
I'm pretty sure.
Good. Well, and that's good because that certainly simplifies it. So, naively, if my naive thing were right, then it would be just L to the 6 here and none of that junk.
Maybe L plus 1.
Well, right. If you're saying, if you're doing P1 bundle, that will be extra L plus 1. Well, that certainly would be good. Why does this imply that L is a zero divisor in the Grothendieck ring? Well, for this, I need to argue that xw minus yw times L squared minus 1 L minus 1 is not equal to 0. This is not an obvious statement at all, but fortunately, all the hard work has been done. So the point is that this class is not 0 modulo L, because it's a difference of, so if this was 0, this would be 0 modulo L, which would imply then that xw is equal to yw modulo L. And then by theorem of Larsen and Luntz, which itself is heavily based on the weak factorization, you would see that xw and yw would be stably birational. And I argued that they were not. So it's not that there's no hard work in there. It's just it's all been done, right? All right. So that's the Grothendieck ring story. Yes.
They also by the cut and paste thing as well.
Oh yes, right. So there's also another thing, which I didn't notice it. I mean, this was pointed out to me by Evgeny Schinder, is that the same example also gives a counterexample to something called cut and paste conjecture. So the way cut and paste conjecture works is as follows: you have two varieties which have the same class in the Grothendieck ring. You ask yourself, can you just chop them up into pieces and rearrange to go from one to the other? And the trouble with it is that you don't know, because the equality in the Grothendieck ring can be way of putting them in something much higher dimensional, and so it's really hard to tell, right? And so what happens here, if you look at xw times c6 times gl2 and yw times c6 times gl2, they're the same in the Grothendieck ring, but they're not even birational to each other, so certainly you cannot do the cut and paste. That's right. Going way back, Gromov had something along the same lines. Right. That's right. That's right. That's right. Yeah. Yeah, it's kind of interesting that something pretty obscure from your symmetry actually ended up being useful in other area. All right. Now, let me explain a little bit more about the generalizations to higher dimensions and what that entails. All right, so first generalization. So n instead of 7. So you do xw now inside n-dimensional odd, and yw is in pw. But this one is singular along locus of forms of rank less than n minus 3. So if we want to do any kind of comparisons, we want to somehow learn how to deal with singular varieties in the context of mirror symmetry. And it's been worked out by Bacharev in the following form. There is something called stringy Hodge numbers of yw. The way it goes is as follows. You take a log resolution. So you have exceptional divisor with discrepancies alpha I, alpha j, I guess. And you define something called the stringy E-function, what it is, you look at over all subsets in the set of indices. Then you look at Hodge-Deligne polynomial. So this is something that's using the mixed Hodge structure on this open stratum. And then you weight with certain rational functions. And what these factors are all about is the following. You have a smooth variety, and you're interested in its Hodge numbers or in its E-function. But for whatever reason, somebody evil gave you not this variety, but its blow-up along some locus of codimension k. So now you want to write the Hodge numbers of the one downstairs in terms of the Hodge numbers upstairs. Then what happens that the points on the exceptional divisor have to be divided by the fiber, by the projective space in the fiber. This is where this comes from. So as an upshot of big factorization or motivic integration, if you prefer, this construct doesn't depend on the choice of the resolution. And as a result, it gives you a well-defined invariant of the variety y. And in case if it's polynomial, you call the coefficients the Stringy Hodge numbers. So to be able to do it in our case, I need to find the resolution of this Pfaffian variety in PW.
Are the discrepancies?
Yes, they are the discrepancies of the GJ. Right. Right. And what this stratum is, I'm looking at intersection of the J's in of the DJs in the set. So it could, if it's empty, it's a big stratum. Right. So to be able to calculate this for the Pfaffian variety, I need to know something about resolutions of Pfaffians. And these are given by something called spaces of complete skew forms. So something rather classical. The idea is the following. Let's say you have this projective space, P wedge 2 V dual. So these are all skew forms on V. Now, this is stratified by ranks of the form, right? So the generic rank is n-1 and so on. So there's some kind of stratification. What you want to have instead of this stratification is some kind of simple normal crossing divisors. I mean, the trouble with stratification is the closures of the strata are singular along the smaller strata. So that's kind of annoying. And what you do, you start blowing them up from lower dimensional strata up. So you start by blowing up rank 2 forms, just the Grassmannian. Then you blow up the proper preimage of rank 4 forms, then proper preimage of rank 6 forms, and so on. And the magic of it is that it stays smooth all the way. And once you do that, you get a smooth variety, which as a set looks as follows. So you look at collections of flags. So I'm just going to write what happens when you. So you look when you. I'm interested in the Pfaffian, so I don't want to do all the blobs. I stop one early. And what you get is you're looking at flags inside V, where F0 has dimension 3. Sorry, FL is V. And there are possibly intermediate subspaces, but maybe not. And in addition, there are WIs in Fi plus 1 in which 2 fi plus 1 over fi dual, which are non-degenerate. So somehow what happens is the big stratum is just non-degenerate skew forms on the quotient by 3-dimensional space. But if the form starts to degenerate, it tries to sprout additional flags in the middle, and overall the whole thing is simple normal crossing divisor. And but there's some combinatorics going on. Unfortunately, there is some inductive structure to it. So if you look at fibers over some previous laws, say they kind of look the same way. So there is some inductive calculations that we need to do here. But we were able to, basically using the same idea. You write the same Cayley hypersurface. You instead of working the Grothendieck ring, I just calculate the stringy E-functions. And you pass to the frame bundle. And you have to look at contributions of Plucker cuts of Grassmannians with different ranks. And they turn out to work the same way as contributions of the singularities of the corresponding locus in the Pfaffian. So it's a bit of a miracle that it works out. And for even n, it doesn't quite work out for whatever reasons. You don't quite have the usual double mirror property there, although I'm sure there's something very similar going on, but it's just slightly novel, so didn't want to deal with it. And maybe I should say something. So what helps here is that in this situation, the singularities are in what I call sort of Zariski locally trivial. So when you do this log resolution, then the fiber over a stratum is so those DJ circle over the images are Zariski locally trivial, and this, as a result, you can just write a function of the singular varieties as the sum over polynomials of strata times some kind of contribution of singularity. I mean, this stuff works for toric varieties. This works for isolated singularities. In general, you may have some kind of complicated monodromy. You can have a singularities, and it moves along the curve, and as it goes back, you get some sort of automorphism, and that will mess up your stringy Hodge numbers. I mean, that makes things more complicated. But you don't have it in this situation, so that helps. And moreover, you see somehow the contribution of points of rank 2i in Pfaffian of in YW is something like this. So there's an extra polynomial, which is very simple. So it certainly indicates that things are nice there. So there's some. You really want to categorify it somehow. You don't just want to say that you have equality of Hodge numbers. That's boring, right? You really want to say some kind of relation between the vector spaces. What sort of relation you expect for vector spaces? You don't expect an isomorphism. That would be wrong. This should be some kind of version of Ruan's conjecture, that there should be some kind of flat family with a flat connection that would interpolate from one to the other. So, and that's how physicists view it. For them, you have this family of n equals 2 superconformal field series, and there are some Kähler parameters there. And then in one limit, you can identify this with cohomology of Grassmannian complete intersection. On the other side, somehow, some way they get to the Pfaffian. I was never able to understand that part of the story, but it's in the papers of Hori and Tong. All right. So that's fine. So the Grassmannian of higher dimension didn't cause us a whole lot of trouble. But then we started to be interested in this story. So generalization to Pfaffian of 2kV. So now we have k between 1 and n minus 1 over 2. And we have this W inside wedge 2V dual. This is dimension n. This is dimension nk. So technically, the geometry is just fine. Nothing really changes as far as all this resolutions. I mean, it's just the bookkeeping becomes so much harder. So here's where the trouble is. It's not such a big deal to calculate the Hodge numbers of a Plucker hyperplane in the Grassmannian. Basically, you pass through this frame bundle, and it's pretty easy. To make this work, so the hard part is to calculate E polynomial of a hyperplane cut of the locus of forms on, I guess, V dual of rank 2p by a form of rank 2i. So you're forced to consider it. Right? And the trouble is that even doing k equals 2k is kind of directly using this passing to this frame bundle. I did it in Maple. It was about 10 different terms. It was a big mess. Took me a while to fix all the bugs, but then it did work, or so I think. But in general, it becomes a problem. And what we did is we were able to write, after some work, we were able to write recursive relations on it. And what?
Recursion in P or recursion in I? Or in both?
In everything, right? No, I mean it's recursion in P actually, recursion in P. And then after you write a recursion like this, we were able to reduce it to a combinatorial identity. The trouble is that those combinatorial identities were beyond what we could handle ourselves. I mean, these were what's called identities of Q hypergeometric functions. And they're, in principle, should be doable by a computer. But I was never able to make that process work. So after struggling with it for a month, I posted it on Math Overflow. And with kind help from the expert, named Hjalmar Rosengren. You know, I mean, I guess for him this is sort of nothing. So to give you an idea, I mean, so this is sort of the hardest part. That's where, you know, so there are some easier steps, but at the end, this was sort of the last step that needed to be done. And apparently, it's a particular case of some Jane's identity from 1981. You know, so and my guess is.
What is the context of that idea?
Well, so this is you know, there's a subject as old as algebraic geometry apparently, where people just write various summations and manipulate them. And there's a wonderful book called Basic Hypergeometric Functions, where basic means base Q. I mean, that's and You know, it's an identity of the, I think, hypergeometric functions of type 543, and it reduces it to 523 with a different parameter. I mean, these are all hypergeometric functions. I mean, the good news is that they're what's called convergent. I mean, there's all finite sums, so I don't have to worry about convergence or any of it. And also this, by the way, this, I really don't care if n is odd here. I mean, this works perfectly well. So clearly, I mean, the point, with even n, you just need to figure out how to make a geometry get into this formula. Yeah, so, you know, I learned a lot about those cubic hypergeometric functions, but still not good enough. I mean, you know, at some point, I basically, you know, asked him, you know, to see if he could prove that. And just after a day, he said, "Oh, this is look at this exercise in that book. I mean, and it quotes that paper, and you pick the parameters this way. I mean, this is what you get." After some what he called obvious symmetries, you know. No, I mean, but actually, the funny thing is at the end there is no computer calculation in the whole proof. I mean, everything I honestly checked by the reference. It also sort of. There's you know Doron Zeiblger's algorithm, which kind of looks at certain recursions, as in this case, I guess k would be changing, and it's some kind of clever telescoping trick. In theory, one could try to see that on the left and on the right, you get the same recursion as k changes. I try to plug it into Maple. I get a page worth of a recursive relation on one side, and so I figured, well, I don't want to deal with it. But you know, it all worked out at the end. Now, the next thing we're interested in is proving that elliptic genera of xw and yw are the same. This will require a completely different technique because elliptic genera, they're not additive on strata, so I cannot do this cut and paste thing. I would have to probably, could still use Cayley hypersurface in some way, but I would have to be more creative trying to recover elliptic genera, and I don't know how to do that yet. What I'm ultimately interested in is trying to construct vertex algebras so that this HPQ strings are dimensions of those whole chiral rings of those algebras. So on one side it should be some kind of ad hoc deformation away from the cohomology of chiral-Durand complex, and I'm not even sure what to make of chiral-Durand complex on the singular side. So, and I couldn't even do it for n equals 7. All right. So, but the hope is that if you really understand the higher dimensional case, maybe that will give you an idea of what you need to do in lower dimensions. All right, this is a good place to stop, which I'm going to do.
Are there any questions?
Can you say something about difference of xw and yw in the Grothendieck group?
Oh, for higher dimensions?
Yeah.
Yeah, I mean.
And higher k.
So the problem is that it's not xw and yw. It's some kind of weighted sums of various loci of xw with various singularities, right? But yeah, otherwise there is absolutely, it would be the same thing, right? Q is just the L, basically.
In this formula.
So yeah, it's going to be, so some kind of weighted things would, yes. So some kind of weighted some kind of weighted class of xw, yw would be annihilated by some polynomial. It's fine.
Is it possible to define some kind of stringy class of a singular variety?
Yeah, I mean, so here's the thing, right? I mean, what the trouble, I mean, as you see, is the denominators, right? So if you localize at these guys, then you can. Well, rather localize at the classes of CPKs. So of course you can, right? But if you don't localize, then it may not be possible. It's hard to tell hard to say how you would do it. Yes. Mm-hmm.
From this formula, you remove the E and all the U's and V's, so it will be an element in some completion of the Grothendieck, right?
A localization. I mean, you just localize. Yeah.
So it's a materic integral of what? Of y. That's why it's independent of the resolution.
Yeah, I mean, It has originally been defined using Mativik integration, using the jet bundles and so on. But for me, a better argument is the weak factorization. You just check that it doesn't change under the blowup, and that's that.
This may answer Sasha's question of what is the stringy class. You just remove the E and instead of UV you write L, and I think that is the stringy class.
My interest in Grothendieck ring is very tangential. I wasn't even thinking about it. It's just I happened to have read Galkin-Schindler paper, and so this was in the back of my mind when we were doing these calculations in Anatoly, and I realized that even though we're getting inequalities of the E-functions, all we were doing is in Grothendieck ring. That's what that is.
In the original example, if you just change the dimension of W, you will lose the Calabi-Yau property. But still, you can make a computation with the KV hypersurface, and you don't get an identity of a similar form.
That's a good question, right? Right, that's a good question. So you could, let's see. So on one side, I'm going to get some kind of fun, and on the other side, I'm going to get a general type. Let's say so I get some four-dimensional Fano and the general type on the other. I mean, I may have trouble I would have some kind of identity. I may have trouble proving that the difference is somehow zero. I mean, so I wouldn't know how to do that. So there would be some kind of relation.
But no factorization of it.
I haven't tried. A priori, I would imagine that I would have something very similar. But I'm not sure if I might get different examples of something that's killed by L, but it may be difficult to prove. It may look something like, okay, I have this Fano variety, and I have this surface, and I have the class of Fano minus class of surface minus some polynomial of L is annihilated by, and yeah, it's probably model. It might still work. But I would have to look at this. It might still work. Actually.
You probably have to know that the fun is not rational in this case.
It may be tricky.
Yes. Yeah, so if you go to lower dimension instead of higher, to n equals to 6, then actually what you get by this, you get K3 surface on the cubic fourfold.
That's right. That's right.
The Pfaffian cubic fourfold.
That's right. It's right. In that case, yes.
Basically zero. So.
Right. It is zero. Right. Yeah. No. I know. What you mean.
Yes. Just only raise it.
Right. That's right.
And so imagine that you have a pair of derived equivalent K3 surfaces.
Right.
So if you take their difference in the Grothendieck group, you expect it to be annihilated by
a polynomial in L? Well, I think it's a very reasonable conjecture, yeah. I mean, I just, I'm not.
Like
yeah.
Surface of degree 12 sections of orthogonal class.
We should try. I mean, a lot of them are given by complete intersections. And so the geometry is very simple. So,
the answer from the back row is yes.
Okay.
Well, before we thank the speaker again, let me just make a couple of announcements. At 3:30 there will be tea, so make sure to get your badge if you would like to. And we'll resume at 4 o'clock. Okay, thank you.